Hey everyone, and welcome to The Explainer. So today we're tackling a real-world problem that has literally haunted students, scientists, and pretty much anyone who works with data. We're talking about calculating massive averages. Imagine you're looking at data from hundreds of students or, thousands of weather reports. Finding the average usually means adding up this endless sea of numbers and spending all night doing tedious, mind-numbing arithmetic. But what if I told you there are mathematical cheat codes, shortcuts that can literally shrink mountains of data into simple, single-digit mental math? Sounds pretty good, right? Well, let's dive in.
Here is our roadmap for today's journey into ultimate mathematical efficiency. First, the power of averages. Second, grouping the chaos. Third, the direct method. Fourth, the assumed mean shortcut. Fifth, the step deviation cheat code. And finally, choosing your weapon.
All right, part one, the power of averages. Okay, so at its core, a mean or an average is really just a single number trying its absolute best to represent a whole giant crowd of data. But let's be honest, raw, ungrouped data can be terrifying. Take a look at this. Here we have 30 students taking a 100-mark math test. You've got 3 students getting 36, 4 getting 40, and so on. Even with just 30 kids, looking at all these individual numbers and frequencies is, well, it's messy. Now imagine if this was a table for an entire city of students. Multiplying each individual mark by its frequency and adding it all up, that is basically a guaranteed recipe for a calculation error. Which brings us to part two, grouping the chaos. To avoid that endless, tedious multiplication, our very first step is to tame the data. We do this by grouping this chaotic mess into neat little buckets, like, say, students scoring between 10 and 25, or 25 and 40. Doing this shrinks our table down significantly. But here's the catch. You can't multiply a bucket, right? If a student falls into the 10 to 25 interval, what actual number do we use to calculate our mean? Well, we need a numerical spokesperson for that group. We call this the class mark, represented by the symbol xi. Because we can't individually talk to every single number inside that interval, we just find its exact middle to represent them all fairly. And finding that spokesperson is incredibly simple. It's like a 3-step recipe. You take the top number of your bucket, the upper class limit, add it to the bottom number, the lower class limit, and just slice it right in half by dividing by 2. So for that 10 to 25 interval, 10 plus 25 is 35, divide that by 2, and you get 17.5. Boom. That 17.5 is now the official representative for that entire group.
Moving on to part 3, the direct method. Now that we've grouped our data and appointed our spokespersons, we can actually use the direct method. Now, I know the formula looks a bit fancy with those scary-looking sigma symbols, but actually, scratch that. Don't let it intimidate you. Sigma literally just means add them all up. This is just the basic average principle wearing a clever disguise. You take the frequency, which is the number of people in the bucket, multiply it by our xi spokesperson, add all those products together, and then divide by the total number of people. It's direct, it's highly logical, and honestly, it works perfectly.
But let's look at a real-world case study to see where this direct method really starts to sweat. Here we have a table showing the number of wickets taken by 45 one-day cricket bowlers. Notice anything? Our class intervals are huge here. We're talking 20 to 60 wickets, 150 to 250, all the way up to 350 to 450 wickets.
Now, think about finding the class marks for these massive intervals. For that last group, the midpoint is 400. That means you'd have to multiply your frequencies by 125, by 200, by 300, and by 400. Imagine doing that manually on a piece of paper during an exam. It's painful, right? It takes forever, and the bigger the numbers get, the more likely we are to make a totally avoidable multiplication mistake. So you gotta ask yourself, isn't there a smarter way?
And that brings us to part 4, the assumed mean shortcut.
To totally bypass those massive numbers, we are going to use the very first major upgrade in our statistical toolkit, the assumed mean shortcut. Here is the brilliantly simple logic behind it. Instead of working with giant numbers, what if we just guessed the average right off the bat? We pick a class mark somewhere right in the middle of our table and just confidently call it our assumed mean, or A. Then we temporarily shift our entire baseline. We subtract our assumed mean from every single class mark. We call this new result the deviation, or DI. Essentially, we're just calculating how far off every other number is from our guess, which drastically, beautifully shrinks the numbers we have to work with.
Take a look at this. Notice the 4th column here, the DI column. In our cricket bowler example, we went ahead and chose 200 as our assumed mean A. Look at how assuming a mean of 200 basically does a magic trick on those huge values. Our class mark of 40 becomes minus 160. Our class mark of 300 drops all the way down to just 100. We've successfully made our numbers way smaller. But wait, we still have a few 3-digit numbers hanging around to multiply, right?
So let's level up again. Part 5, the step deviation cheat code. Which naturally leads us to ask, can we push this even further? Is there an even faster way to handle those lingering 3-digit numbers? Well, look closely at those deviations we just found. Minus 160, minus 120, 100. Do you see it? They all share a common factor. Because our class intervals have a uniform, steady gap or size, which we call h, all our deviations are perfect multiples of that size. In our cricket example, the class size h is exactly 20. So, to find our step deviation ui, we just divide all those pesky deviations by 20. By scaling them down by their common gap, we completely unlock the power of easy mental math. Okay, just look at the absolute magic happening in these last two columns right now. We divided those scary deviations by 20. Minus 160 instantly became minus 8. Minus 120 became minus 6. 100 became just 5. Now to find our average, look at the very last column. We are quite literally just doing simple single-digit times tables. 7 times minus 8 is minus 56. 5 times minus 6 is minus 30. What used to be a horrifying 3-digit multiplication nightmare is now something you can literally do effortlessly in your head. To finish the puzzle, we just have to undo the scaling cheat code we used. First, we find the mean of our tiny new scaled numbers, which simply adds up to minus 106 divided by 45 bowlers. Then, we take that fraction and multiply it back by our class size of 20 to undo the division we did earlier.
After doing that really quick bit of math, we get negative 47.11. But remember, at the very beginning of our shortcut, we subtracted an assumed mean of 200, right? So to get our true, totally accurate average, we just add that 200 back at the very end. 200 minus 47.11 gives us our final, perfect answer, 152.89 wickets. We just solved a massive data problem with absolute incredible efficiency.
Finally, part 6, choosing your weapon.
So now that we have these 3 distinct tools in our belt, how do they actually relate to one another? Look at the 3 formulas side by side right here. While they might look increasingly complex, here is the secret. They are mathematically identical. The assumed mean just temporarily subtracts a, then adds it back. Step deviation subtracts a, divides by h, then multiplies by h and adds a back. They all achieve the exact same goal, yielding the exact same true mean. They are basically just different lenses for looking at the exact same truth.
So, when you are staring down a problem, how do you choose your weapon for maximum efficiency? Here's my most practical advice for you. Use the direct method when your numbers are tiny. Like if the frequencies and class marks are just 2s, 3s, and 5s, don't overcomplicate it, just multiply them directly. But the moment you see a table that looks absolutely terrifying, with huge intervals and massive numbers, unleash the step deviation method. Yes, for sure, it requires writing down a couple of extra columns, but it completely removes the risk of making huge calculation errors by turning massive data sets into easy, highly accurate mental math.
I really want you to remember this. Math isn't about memorizing scary formulas just to torture yourself. It's about finding the smartest, most efficient path to the truth. Statistics shouldn't cause you anxiety. These formulas, they aren't designed to punish you. They are literally shortcuts invented by brilliant mathematicians to make your life easier. They are just powerful tools in your toolkit. But before I let you go, I want to leave you with a bit of a provocative thought. Throughout our entire step deviation cheat code just now, we relied heavily on dividing by h, the uniform, perfectly equal gap between our class intervals. What do you think happens if a dataset has unequal class sizes? Can we still use our cheat code, or does the math just totally break down? Think about the limitations of these formulas and keep questioning, keep exploring. Thanks so much for joining me on The Explainer today, and I'll catch you in the next one.
Hey everyone, welcome back. Today, we're putting on our detective hats and tackling Chapter 13, Statistics. Now, I know stats can sometimes look like a giant wall of scary numbers, but honestly, by the end of this explainer, you're gonna crush it. No fear, I promise. We're gonna take all this complex math and turn it into really simple visual clues, transforming abstract numbers into a real-world masterclass in problem solving. So, here's our game plan for today. First, we'll uncover the mystery of grouped data. Then, we'll visit the mode neighborhood, roll the cumulative snowball,
hunt down the median, and finally, pack up our statistical toolkit. Let's jump right in.
Section 1. The mystery of grouped data. From open clues to hidden numbers.
Okay, let's dive into this. Think back to 9th standard for a second. You actually already have this incredible intuition for basic stats, right? You know what mean, median, and mode are when the numbers are just sitting right there in front of you. Finding the mode for ungrouped data, it's like finding a clue lying right out in the open. It's just the most frequent observation. Like, if we look at this bowler's wickets across 10 matches, you just scan that bottom row for the highest number of matches, boom, right there, 3 matches. And how many wickets did they take in those 3 matches? Exactly 2. So your clue is out in the open, and the mode is simply 2.
But here's the real mystery we're solving today. What happens when the data groups up? In group data, those exact statistical numbers aren't just sitting out in the open anymore. They're hiding inside these broad class intervals. So instead of knowing exactly how many wickets or marks someone got, you only know they live somewhere in a specific neighborhood, like, say, between 10 and 20. To find the exact mode or median now, we need our detective formulas to really zoom in on those neighborhoods.
Which brings us to Section 2, the mode neighborhood. Pinpointing the most popular.
So here's our first real detective tool. We need to shift from just pointing at one single number to locating the modal class, or what I like to call the most popular neighborhood in town. And this formula right here is the tool we use to do it. Okay, don't panic. I know it looks like a terrifying jumble of letters and fractions, but I want you to look at it differently. This isn't just random, scary math. It's actually a really logical treasure map designed to guide you straight to the exact hidden mode.
Let's break down these variables using our neighborhood analogy. L is simply the lower boundary of our popular neighborhood. H is how wide the street is, basically the class size. Now for the houses, the frequencies. F1 is our target house. It's the one with the highest frequency. F0 is the neighbor right behind our target, and F2 is the neighbor right ahead of it. See? It's not so bad. You're just looking at a house and its immediate next-door neighbors. Now what's really cool is how easily we can use this map. Take a look at example 5 here, a survey of family sizes. To find our target neighborhood, we just scan for the maximum frequency down in the bottom row. The highest number of families is 8. So that means our modal class, our target neighborhood, is family size 3 to 5. Let's map this out, step by step, like we're building a case on a whiteboard. Our modal class is 3 to 5. So L, our lower limit, is 3. The class size, H, is 2, since 5 minus 3 is 2. Now for the houses. Our target frequency, F1, is 8. The neighbor behind it, F0, is 7. And the neighbor ahead, F2, is 2. You see what we did? You literally just pulled the numbers straight off the table and plugged them right into our map.
And when you do the math, subtracting the neighbors and multiplying by the street width, you get 3.286. We did it! We successfully zoomed into that broad 3 to 5 neighborhood and found the exact hidden peak. The mode of this data is 3.286.
All right, so the mode finds the most popular value. But as a detective, sometimes popularity doesn't matter to you. Sometimes you need to find the exact dead center middle of your data, the 50th percentile. So how on earth do we find that when the data is hiding inside groups? That takes us to Section 3, the cumulative snowball, preparing for the median. To find that exact middle ground, we need a totally different technique. We have to prep our data using what I call the cumulative snowball. Imagine a snowball rolling down a snowy hill. Up at the top, in the 0 to 10 marks class, you've got 5 students. As the snowball rolls down into the 10 to 20 class, it picks up 3 more students. So now the snowball has 8 students packed inside it. It rolls down to the next class, picks up 4 more, making it 12, and it just keeps accumulating. This running total, that's your cumulative frequency. If we want the official textbook definition, cumulative frequency is exactly that, the frequency obtained by adding the frequencies of all the classes preceding the given class. But honestly, conceptually, just picture that snowball rolling down the table, getting larger and larger until it holds every single piece of data by the time it hits the bottom.
Moving on to Section 4, Finding the Median, Locating the Middle Ground.
Okay, now that our snowball contains all our data, we can use it to pinpoint the median class, the exact neighborhood where our middle student is hiding out. Here's the critical setup step. First, we find the total number of students, n, which is 53. If we want the exact middle, we just slice that in half. 53 divided by 2 gives us an n over 2 of 26.5. We are actively looking for student number 26.5, but which class are they in? Where are they hiding?
To find out, we take that 26.5 and look over at our rolling snowball, our cumulative frequency column. We're looking for the very first snowball that is actually big enough to hold 26.5 students. 22? No, too small. But look at the next class. It has a cumulative frequency of 29. 29 is greater than and nearest to 26.5. So boom, the 60 to 70 marks range is our median class.
And this brilliantly sets up our next tool. Once we've cornered that median class, we use this formula to zoom in. Similar to the mode map, it uses the lower limit L and class size H. But here, we swap in our middle target N over 2, the frequency of our median class F, and, this is super important, the cumulative frequency of the class right before it, which we call CF. Let's plug the numbers in together so we're all on the same page. Our lower limit L is 60. Our middle target N over 2 is 26.5. The snowball right before our class CF was 22. The frequency F of our median class itself is 7, and our class size H is 10. We subtract 22 from 26.5, divide by 7, multiply by 10, and finally add it all to our base of 60.
And here is the crucial payoff. We get 66.4. This is an incredibly powerful number. It tells us that exactly half of all the students in this entire data set scored below 66.4 marks, and the exact other half scored above it. We found the absolute perfect middle.
Section 5, your statistical toolkit. Let's do a quick chapter summary.
Let's bring this all together. You guys have mastered some seriously heavy mathematical machinery today, turning abstract, messy data into solvable mysteries. Let's review your brand new toolkit. Number 1, you have the mode formula, your neighborhood map for pinpointing the most popular data point. Number 2, cumulative frequency, the snowball method to track running totals. Number 3, the median formula to find that exact middle target. But hey, remember the golden rule right from section 13.5. Before you use any of these tools, you absolutely must ensure your class intervals are continuous. Without an unbroken street, your neighborhood map just won't work.
So you're no longer just looking blindly at grouped data. You're dissecting it. Now that you have these statistical superpowers to find exact truths hiding inside broad, messy groups of information, what other mysteries in the real world will you solve with data? The numbers are out there waiting for you. Keep analyzing, keep calculating, and I'll see you in the next explainer.
Welcome to this explainer. Look, as a veteran board evaluator, I am going to show you exactly how to extract every single mark from the statistics chapter on your upcoming Karnataka SSLC exam. Now, I know you already know what a mean, median, and mode are. You've done the homework. But today, we aren't just doing math. We're cracking the code of the 81E and 81K evaluation papers. I'm going to show you exactly what examiners like me are actively looking for when we grade your answer sheets, and how you can absolutely maximize your score, even if your final calculation goes a little off track.
So here's our roadmap for today's explainer. 1. Inside the evaluator's mind. 2. Mean securing step marks. 3. Mode, the formula goldmine. 4. Median, the cumulative trap. And 5. The evaluator's final checklist.
All right, part 1, inside the evaluator's mind. Let's talk about the half-mark hack.
Let's pull back the curtain for a second. You know, we, evaluators, we actually aren't out to fail you. In fact, we're literally hunting for reasons to give you points based on the official key answer schemes. Every April, it breaks my heart to see students lose incredibly easy points. They panic, mess up a mental calculation, and just cross out the whole page. No, listen to this rule. Even if your final answer is totally wrong, a perfect formula and table will guarantee you passing marks. Show your work. It's really that simple. Board exam marks are heavily segmented into step marks. Never, ever leave a step blank. A blank page gets a 0, right? But a beautifully drawn frequency table? Bam, you're on the scoreboard instantly.
Moving on to Section 2, Mean, securing step marks, specifically focusing on the assumed mean method.
Now, for your 3-mark written questions, the assumed mean method is an absolute favorite for examiners. Seriously, take a good look at this official SSLC key answer sheet on the screen. See that right-hand margin? Boom! A massive 1.5 marks awarded purely for calculating the table values correctly. Think about that. That is half of the marks for the entire question, handed to you before you even touch the final formula.
So setting up a pristine, organized table structure exactly like this, with explicit columns for your class marks, frequencies, deviations, and that final product of frequency and deviation is your absolute first step to locking in those points. Grab a ruler, draw the actual lines. When an evaluator sees a clean table where your DI equals XI minus A is clearly calculated, I'm telling you, our pens automatically start hovering over that tick mark. We love to see it.
Which brings us to an absolutely crucial point. Always write the exact formula down before you start substituting any numbers. The assumed mean is x bar equals A plus the sum of Fi times Di divided by the sum of Fi. Just writing that simple equation alone secures another half mark according to the official grading rubric. So do the math. You now have 2 out of 3 marks and you haven't even done the tricky final division yet. Crazy, right?
All right, let's hit section 3, mode. I call this the formula gold mine.
Look, finding the mode is arguably the fastest way to score 3 quick marks on the entire paper. But, and this is a big but, only if you avoid the classic evaluator traps that catch students out year after year. Here's the absolute biggest mark trap I see constantly. Students are rushing, and they accidentally swap the preceding frequency with a succeeding frequency during substitution. So remember this simple high-yield memory aid, okay? 0 comes before 1, and 2 comes after 1, right? Therefore, F0 is the class right before your modal class, F1, and F2 is the class right after it. Lock that sequence into your brain.
Now, when you're laying out that mode formula, I need you to focus really closely on the denominator. 2 times F1 minus F0 minus F2. Simple arithmetic errors right here, especially with those negative numbers, will instantly cost you a full mark. So take an extra 5 seconds. Literally just pause and double check your subtraction here. The evaluator really wants to give you these marks, so please don't give us an arithmetic excuse not to.
If you want the points, just follow this exact 3-step sequence on your paper. First, clearly identify and write down the modal class. Second, explicitly write out the mode formula. And third, substitute your values without swapping those frequencies we just talked about. If you lay your paper out exactly like this, evaluators will just effortlessly glide through your answer, awarding you full marks along the way. It's really all about making your competence totally visible to us.
Okay, let's jump to section 4, median, the cumulative trap. Now we're entering the danger zone. The median is where the highest number of students just bleed unnecessary half marks, and it's honestly almost entirely preventable. Let's look at another official key answer to see exactly why. Pay attention to that right margin again. Notice how just adding that extra cumulative frequency column to your given table secures a crucial half mark. You literally just add the numbers up diagonally and boom, you are on the scoreboard. Never ever skip drawing the table in your actual answer booklet.
And here is the linchpin. Calculating this single fraction correctly, n divided by 2, is the mandatory key to finding the right median class, which basically unlocks the rest of the problem. If your total frequency n is 100, write down n over 2 equals 50. Then, immediately go find the cumulative frequency that's just greater than 50. That right there defines your median class. If you rush and get this wrong, well, all your subsequent values, your L, CF, F, and H, they'll all be completely wrong. Just look at this exact points matrix for a median question. Table, half mark. Finding n over 2, half mark. Writing the formula itself, half mark. Proper substitution in the final answer, 1.5 marks. This proves that even if exam pressure hits and you totally mess up the final decimal division at step 4, you still walk away with 1.5 marks. Never, ever give up on a statistics question halfway through. The steps are literally worth gold. Finally, section 5, the evaluator's final checklist. Let's summarize for exam day.
All right, to walk into that SSLC exam room with total unshakable confidence, I need you to execute these simple formatting rules. Draw those clear, ruler-line frequency tables. State your formulas explicitly before you write down a single number. Carefully label all your variables off to the side, your F1, CF, H, so the evaluator can clearly see what you've identified. And please, double-check that denominator arithmetic. If you do this, you make the evaluator's job so incredibly easy that they'll be thrilled to give you every single mark you've earned.
So I'll leave you with this. Will you let a simple formatting error steal your hard-earned half marks, or will you use this blueprint to claim every single point you deserve? Take this evaluator's mindset with you into your SSLC mathematics exam. Just remember, every single step you write is a scoring opportunity. Show your work, write clearly, and go secure those top marks. Good luck.
You've absolutely got this.